Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like,
was that designed by AI?
And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and today's episode is about robot design. I'm finding out how roboticists develop new ideas for robot designs and how they're making use of new developments in artificial intelligence to help design robots that are smart, adaptable, and robust. Before that, I'd like to remind you to rate this episode and leave a review, if that's something you can do on the platform you're listening on. Another way to support the podcast is to share new episodes on social media or tell your friends about it. It really helps me reach more listeners, so thanks in advance. This episode is powered by the Advanced Research and Invention Agency's Robot Dexterity program, which aims to transform robotic capabilities and unlock a step change in human productivity. ARIA funds research that's right at the edge of what's currently possible across the full spectrum of science and technology. To explore the work they're currently funding, find out about new funding opportunities, and share feedback on their upcoming research programs, check out their website at aria.org.uk. So, without further ado, I'm excited to introduce this week's guest. I recently had a really interesting chat with Josie Hughes from EPFL about using AI to develop new designs for robotic manipulators. This week, I'm speaking to Josie Hughes, an assistant professor at EPFL, whose work focuses on developing novel designs for robot hands and manipulators. Hi Josie, wonderful to have you on the podcast.
Thank you. Thanks very much for having me.
So you lead the Computational Robot Design and Fabrication, or CREATE Lab at EPFL. So can you give us a little bit of an overview of the research that you do in your lab?
Yes, of course. So it's a bit of a mouthful, the title.
Most of them are, don't worry.
But largely we're interested in how to design physically intelligent robots. So robots that can go out into the world and robustly operate in different environments and scenarios. From traversing the Swiss Alpine environment to performing dexterous manipulation in a cluttered environment. So we're really interested in robustness and how that arises from the body and what we see as embodied intelligence. So the way that we see in biology, animals, plants offload computation to the body to enable possibilities in terms of robustness or otherwise that are not possible. So how, if we can design this intelligence, we can then combine it with control AI to show things that could not be possible with pure control or AI methods.
Fantastic. Can you give maybe one or two examples of kind of areas that you're working on at the moment?
Absolutely. So we've been working in soft robotics for a while. So looking at how do we introduce compliance into structures. And I think compliance and stiffness is really important and something we see across biology. We don't see very many purely rigid structures. So if we look at the human hand, we have a mixture of rigid bones and a load-bearing skeleton structure with softness in our skin and our ligaments and tendons. So, for example, in manipulation, we've been looking at how do we mix together these rigid structures with softer, more compliant ones and how that can give rise to both dexterity, but also more precision. We're also looking at ways that we can use softness and compliance in other ways, for example, for morphing, how we can have structures that can physically adapt on demand or in response to the environment. And then one thing I'm really interested and excited about is the idea of growth, because I think all our robots are static at one instance in time. But if we look at anything in nature, it's completely continuously evolving in respect to time, be it in the fact that cells are dying and regenerating, through the fact that we're growing over longer time periods, and we see many examples of morphing or adapting through time. So I'm trying to look at different ways we can introduce these mechanisms into our robots through mechanical principles or other, and then combine this with control to show more robust or new behaviors that we can't achieve otherwise.
Mm-hmm. You've mentioned quite a lot, the comparisons with nature. How much inspiration do you get from nature in your work?
I think a lot. I think it's a really compelling, it's a benchmark. I think we still see very few cases outside of a really constrained environment where robots can actually outperform humans or other animals in a meaningful way. Down to simple, like a crow, so intelligent in the way they can use tools. Yeah. But we can't get the robots in some ways to show some of this, maybe not on the computational side, but in the way that we physically interact with the world. So I think they give great benchmarks, source of inspiration, mechanisms. But at the same time, we're not bound by biology. So we can use it as inspiration, but also think of what can we do that we don't see in nature. And manipulation, I think, is a really good example of that. So humans, we have 4 fingers and a thumb. Doesn't necessarily mean our robots need to have that. So I think it's looking at nature for inspiration, but equally we are using a different set of materials, resources. We don't have homeostasis. We don't have metabolism yet for our robots. So we do need to think a little bit broader than just biomimicry.
Yeah. There are different opportunities and different limitations, I guess, with robotics. So theoretically, you can do things that animals can't. But maybe we'll just try and get to what they can do first.
Maybe what they can't is sometimes easier than what they can.
That's true. So, you've mentioned a little bit about robot dexterity, and you are one of the creators in the ARIA robot dexterity program, where you're using artificial intelligence to generate task-specific designs for robot manipulators. So can you talk us through how that process works?
Yeah. So it's really exciting to be part of this program, and we're specifically working in the area of co-design. So how do we design a manipulator for a dexterous task, given some information about it? Because we know there is clearly not one universal manipulator for everything. Yes, the human hand has huge capabilities, but still it's not optimal in any sense of the word. And we know for different tasks, there is definitely room for different capabilities. And this could be in terms of the morphology, the placement of sensors, the choice of actuators. Our kind of moonshot, our vision is that we want to be able to go from an image of a task, a video, a text description, and from that to formulate the morphology of the gripper, its controller, its part selection that we can then take, print, fabricate, and then return as a solution into the real world. And really looking at how do we combine reasoning about design from AI with also other computational methods.
Mm-hmm. It's an incredible idea. I think it's just fascinating. With the kind of generative AI that people are familiar with is probably, large language models that they chat to or image generators. And they've been trained on, the vast wealth of the entire internet. What data do you have behind the AI models to kind of know what robot form is going to be good for a particular task?
So exactly as you say, we have these large language models that many of us are using on a daily basis, and these being trained on a vast corpus of data. Now, firstly, this is already interesting for us because that vast corpus of internet data combines lots of inspiration for robot grippers, lots of information on biology, lots of inspiration on other grippers. So that's one thing. So there is some existing context that these models have about some information about design. There is one issue that they are really bad at spatial reasoning. They've got no idea of what's up or down. What does 2 meters mean? What does 3 meters mean? And also in presenting gripper design in some way that's interpretable either to humans or to machine or to simulator. So we're looking at, can we take these large AI models, be it in terms of language, vision, or other ways, which already have this large kind of contextual world knowledge, but then can we fine-tune them, customize them with specific design information? So then taking, for example, existing gripper designs, which we could generate just probabilistically or formulaically, and generating these in a text format. So in this case, URDF, something, a text file format that we can reread in simulation to fine tune these. And then the idea is we combine the best of some information about robot manipulators, which has also some spatial information, with contextual world knowledge about materials, use cases, what a task might be, to try and fuse these together.
I mean, I guess the models also don't really understand physics, right? They don't understand forces or what it's like to interact with physical objects in the world. Do you kind of have to teach them that as well?
Yeah, I think that's an interesting one, because I think it's, how do we understand physics? Because when I drop a ball, I'm not in my head computing, okay, first, second, third Newton's law, but I can have a prediction of what's going to happen. And I think that's the kind of reasoning that we want to see from these foundation models. Now, some ways they can just generate the code needed to do this kind of physics simulation. But what we really want to see is, can we use this intuition of what's going to happen, and how do they capture that? So I think it's an interesting question, and we need to look a bit to humans and how do we reason about physics in some ways, to look at how do we inform our models to also have this reasoning. Yeah.
Imagining you've got a task you want a robot to do. You have a video of the task, you show it to the AI, you say, make me the best robot gripper for this. It will spit out, I guess, a few different ideas, and then you start trying them. Do you rule out some of them immediately because they're ridiculous? Or?
Very, very good question. So what we are doing at the moment is we're taking some initial design ideas from our AI reasoning element, and we have that in a wider pipeline, and we're combining this with simulation and reinforcement learning to do what we're calling local optimization. So we have these high-level different grippers, which might have very different numbers of fingers, very different varied topologies, and we take these variants and we train policy for control, and we evaluate the performance on the task in simulation. And using that, we then measure their relative performance, and we also take that video of the simulation and give it back to our large language model to have a second stage where they can refine and improve. This then goes back to our local optimization in reinforcement learning through simulation. So we're combining the really ungrounded large language model with grounding somewhat to the real world through simulation. So actually evaluating these. And then eventually, after so many iterations, we have a reward function that's so high, we want to fabricate these and then take these into the real world, transfer the control policies, but again, get feedback, be it from a human description, video of the performance in the real world. So again, can we loop that back to the foundation model to further improve?
Okay. And how far along with this research are you at the moment?
So we have our first fabricated gripper from this pipeline. So it's still very early days, but we've already at least managed to, for very simple tasks, go from text input to fabricated gripper, and also close this feedback loop through simulation. So we saw promising results in that the combination of large language model and simulation feedback was able to improve the reward, so the performance of the manipulator, and we could fabricate the design and show some feasibility. But we're now looking at broader testing across different tasks. How do we improve the dexterity of the solutions, the range of different hands to really have a first minimal viable kind of product or demonstration of this approach?
Has the AI generated any designs that are completely weird, completely unexpected, that you just thought, whoa, what's this? And then, it performed really well in simulation or anything like that?
So we're still testing, and I think the big challenge is, how do we have this creativity across manipulation? I think they're not designs that we're saying that we would necessarily intuitively say this is what I would design as a human. So I think there's definitely generation of solutions that are just not trivial, but it's still. I think one interesting thing is if we had something like local manipulation, or if we extend the task domain of what we're asking our robot to do, I think we're going to start seeing some really interesting designs that we might not come of, especially as I think we, as roboticists, we have this very artificial division between locomotion and manipulation, which is not something that we see in nature when we widely see animals repurposing manipulators as feet. So I think that's something that if we can break around from our very artificial engineering kind of divisions of this is a locomotor, this is an end effector, to how do we develop robot bodies that use their arms in different ways, from prehensile manipulation to others, I think that could lead to some really interesting and novel designs.
Yeah, that's really interesting. You've mentioned, inputting a specific task and trying to generate designs that are tailored to that task. There's no one size fits all, but how task specific would the final gripper be? Because it's also useful to have something that can do a lot of different tasks. So where is that balance?
Yeah, I think it's a really interesting question. And I think the ideal one would be develop methodologies that can work across both. Because you say sometimes I want to be in this factory line, or I want to harvest raspberries, just raspberries, and I want to do this really well, and I want no overheads, no additional mass, and I'm fine with that. But other times I might want something that's more general purpose, and I might want something that can adapt to tasks. So I think that's very interesting. How can methods work across these? And also, how does this lead to different solutions? Because I think more general purpose and manipulators, maybe we end up something looking a bit more like a human, which would be kind of interesting. Can we see what's happened through millions, billions of years of evolution actually coming through in these algorithms? But equally, I think it's harder to test in certain ways these solutions. Like, what tasks do we pick to test? I think is still very unclear. And choosing things that just don't end up with a kind of a global, if we have a Pareto front, how do we choose where we are on that between different tasks? But one thing I'm also excited about is, what about if we don't have to have just one manipulator? Can we have something that can adapt and grow online? Because I think that could then solve some of these trade-offs in that we can adapt and change online. So if we have tasks that we want to vary between, we can actually do that through online adaptation.
You mentioned a term there that I'm not familiar with. Was it a Pareto front?
Yes, a Pareto front. So if we have a multi-objective problem, rather than optimizing for one objective where we get one solution, if we optimize for a multi-objective solution, we get a surface of solutions, which is then the Pareto front. So I think that's kind of interesting as we go from single objective, one task, to I want to do two tasks, which might have quite different needs. What are the trade-offs there once I have different tasks, and how does this lead to different solutions? What do the different morphologies look like? What are the different actuators required? And what is the loss of performance when we go from task A to task B?
Yeah, that reminds me of this concept in evolutionary biology of like an adaptive landscape, where like you're trying to understand why one thing can't evolve into another thing, and it's because it's really fit in its current form, and there's another fitness peak over there, but there's a valley in between, so all the organisms that would kind of gradually evolve towards that are worse than their parents, so they don't survive.
That, I think it's a really good analogy. I think it's exactly the same kind of behavior we're seeing. Is, are those two peaks too far apart?
Exactly.
That if we then optimize for both, we end up just with a flat kind of front, and it's much lower performing than each of the individual species in each individual environment.
Yeah. Absolutely fascinating bit of research. Another major theme in your research, which we've touched upon a little bit, is soft robotics. And I always think soft robots tend to look really different than people imagine a robot will look. So can you describe some of the soft robots you've worked on and tell us a bit about how they work?
Absolutely. No, I think it's a very exciting creative area, soft robotics, because we're kind of moving away from rigid materials, joints, structures, and we're starting to use new materials, even just new form factors. So, for example, we're working a lot on soft robot arms, so inspired by elephant trunks or octopus tentacles. So rather than having rigid structures, we have continuum structures which can bend in a kind of infinite different configurations and forms, and looking at how we can be both soft and compliant, but also strong and precise, and overcome some of these constraints that we see in soft materials. We're also looking at underwater swimmers, because we see in underwater environments, we have a lot of soft animals, fully soft kind of muscular hydrostrats, again, octopus, starfish, others alongside more skeletal structures. So looking in swimmers in that areas. But we're also looking at some other soft organs that are a bit more unusual. So, for example, the tongue. Which is a really interesting one of huge dexterity, high force requirements, but fully soft. So yeah, lots of different form factors, and looking at both the design and new fabrication technologies for these.
Amazing. Yeah, I definitely want to see more octopus-inspired robots. I think octopuses are just so cool, and like not only their soft dexterity, but the fact that their arms are controlled independently from their brain. Like they're just incredible creatures.
Yeah. No, and I think that's the interesting about soft robotics is it's this tie between body and control. And as soon as we have softness, that enables us to have more decentralized control, like you talked about in the octopus, and really rethinking what control means in terms of robotics, and moving to a paradigm where we want to embrace contact and the environment rather than rigid robotics, which is essentially we want to at all cost have the kinematics we want and have a force such that we kind of overwhelm natural properties. So it's an interesting area.
Yeah, I mean, one thing I've learned doing the podcast, which never would have occurred to me before, was just that idea that, with soft materials, they're much harder to predict. You can't just have like a nice model of exactly how the arm is going to move when you have a motor in it or whatever. And it's kind of maybe embracing that uncertainty a little bit.
Exactly. I think there's lots of advantages that can come from that, and lots of ideas that come out of how do we control, how do we, as you say, embrace this uncertainty, this lack of predictability, and use it in different ways.
Mm-hmm. Are there particular applications you're targeting with this? I know you mentioned underwater robots, but kind of more specifically with your soft robots.
So agriculture is always an interesting one, from harvesting through to other interventions. We just started looking at operation in steep slope viticulture here in Switzerland.
Okay.
So very unstructured environments such as that are really interesting. The medical domain is always very interesting in terms of replicating human physical processes. Mm-hmm. For example, with this tongue, looking at mastication, through to also developing instruments, tools for use in medicine. And of course, through to manipulation, where the inclusion of soft robotic components, if not a whole fully soft robot, can really give us increased robustness and other properties.
Yeah, I guess if you're picking up something very delicate, having a soft gripper is definitely an advantage.
Indeed.
So you've also worked on reconfigurable robots that can change their shape depending on the environment they need to move through. Tell us about these robots and, what are the main advantages and challenges of this approach?
Yes, so I think this is really exciting and within the scope of soft robots, because if we have something that's soft, we introduce the capacity for it to reconfigure itself or to morph into new forms. So one example is we have a compliant rover that can morph from being a ball. So it can roll, we can let it fall, and it survives from great heights to something that's flat where it can drive, locomote, and swim. So it really can introduce different modalities. And I think that's really exciting because now instead of thinking, okay, I need to go around this river, I can just morph and become something that can cross the river rather than having to go around it. So it changes what we can do in terms of planning and how we'd approach problems. So I think that's the real big advantage of reconfiguration, be it across manipulation or locomotion. We could reconfigure our body to be optimal for that task. So simplifying the control. I think that's the huge potential advantage. We can optimize for the environment or task. The big overhead that we have is we need a mechanism for this. We need an approach for doing this. And this can introduce weight of the robot. It can reduce the overall kind of functionality of that robot in one particular environment. I think this is coming back to exactly the analogy you had a minute ago. It's this same idea of we make it more generalizable, general purpose across different tasks and environments, but we can sacrifice something in terms of performance, efficiency at those individual task and environment modes. So I think this is the interesting thing is what's this optimal trade-off between having these morphing capabilities versus introducing overheads, losses through the additional complexity in the physical design and control.
And I mean, how is the reconfiguration controlled? Is it something that the robot triggers? Is it something that, a human in the loop has to trigger? Or is it, even done automatically just by the form of the robot?
I think you nicely cover the different ways we can do it there. So one thing is just to have it passively. So again, embracing this compliance, if we have something that can passively adapt and be compliant to the environment, that gives us already some amount of local reconfiguration just in response to the environment. And we can maybe tune that with variable stiffness mechanisms or others. But then if we have more global reconfiguration, and this could be driven through a number of mechanisms, it could be tendon driven, pneumatic, any kind of actuation source that we can really integrate, then we could be, again, active or kind of automated or learned. And I think there's an interesting kind of control and learning task of how do we learn when it's optimal to reconfigure our body for a given task, and how do we understand the relationship between morphology and task, which is interesting because it really connects to this co-design problem in general. But now we release the constraint of having a single optimal design. We can now have a robot that can move between different morphologies as the task varies.
Yeah. And I mean, one thing that you see with animals in nature is that they have an implicit understanding of how their body works and what it can do and can kind of problem solve and, I don't know, work out exactly the shape they need to be to squeeze through a gap or, stuff like that. that's hard to program into a robot, I guess.
Exactly. And like if animals lose a limb or they have an injury, we can compensate that in our control strategies.
Yeah.
So there's a huge resilience that we have in both understanding our body through proprioception and other senses and then responding. And I think exactly what you say there, one big challenge with these reconfigurable robots is understanding our current state and this proprioception. Because again, we can't make the assumption that we can just use forward kinematics or we can just assume we have this current configuration because we have this uncertainty if we're morphing. The one thing is just understanding our configuration and then to being able to control it. And then if we have a continuous space in which we can morph, then suddenly it's how do we control that? We've got an interesting project looking at the moment, transition between tadpole and frog. And I think this is a really interesting, still hugely complex biological process, but just happens so naturally. But can we understand here what's the change that undergoes in terms of the controller as we have this change in morphology? And can we use that to help inspire controllers for morphing or reconfigurable robots?
That's fascinating, yeah. I mean, I don't know if it's true for tadpoles, but like caterpillars, when they become butterflies, they basically break down into like a soup and then reorganize all of their cells, which just blows my mind every time I think about it.
That's crazy. That's a very good another idea to look into. Thank you.
Yeah. I guess this field of research, there are so many possibilities. It seems hard to even know where to start.
Yeah, I think that's exactly. There's so many examples. There's so many examples from biology. There's so many new technologies that are emerging. And there's a lot, I think, of imagination and creativity we can look to creating up new mechanisms, new capabilities for robots.
Really, really cool. Yeah, very excited to see what you come up with next.
Thank you.
Josie, it's been great chatting to you today. I've been talking to Josie Hughes from EPFL. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. And don't forget to join the Robot Talk community on Patreon if you'd like to support the podcast and get access to some awesome perks, including monthly bonus episodes, behind-the-scenes updates, merch discounts, and more. Visit patreon.com/Claire Asher and join the Robot Talk community today. Next week, I'm chatting to Akti Hainler from Starship Technologies about autonomous robot deliveries. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.